Welcome to Web Handling. My name is Dave Roysum. In this short clip, we explain why your wound roll ends may not be as flat as your customer expects and what you can do about them. I know your time is precious, so let's get started. There are many things that can ruin your roll ends. Some of these I've covered previously on this All Web Handling channel. For example, we have already covered the various causes of feathered or rough roll edges in Wdb20168x, so we need not repeat that discussion here. Also, we have already covered the various causes and types of telescoping in Wdb20168x, so again, we do not need to repeat that discussion here. Those are distinctly different defects that will have distinctly different remedies than what we are going to discuss here. What we will cover here is when the roll is wider at or just above the core than it is elsewhere. As you will see, this is guaranteed by the laws of physics to happen on virtually any and every roll ever wound. There is a lot of diagnostic information in a set of rolls cut from a parent roll. As I detail in a dozen slides of the advanced winding section of my award-winning Web 101 class, you should inspect both sides of every single roll in a set of rolls. If you do that, you should be able to diagnose your specific troubles with much greater reliability. Your roll width will be wider at or just above the core with very, very few exceptions. This is guaranteed by the laws of physics for almost every roll ever wound. This can cause a variety of practical problems, such as poor and dangerous roll vertical stacking or permanent web width increases. Your customer may have other complaints about the rolls not having flat ends. You can and should measure the width of your roll as a function of distance from the core. This is quite simple to do. Merely measure the distance from a straight edge to the roll edge at various radii. Here we show the left edge of the top is inset 3 mm and the right 4 mm for a sum of -7. Towards the middle the sum is -5. At the core the sum is 0. Thus, the bottom of the roll is 7 mm wider than the top. If the roll edge is concave, the sign is minus. You should consider doing this at several distances above the core, at least for the first few times you do this measurement, even though it is the bottom width versus the top width that troubles most customers. As I've said many times, the roll width must be non-uniform. That is because the inner layer pressure coming from winding tightness near the core is greater than the pressure at the middle, which is greater than the pressure at the outside. The pressure is a function of position, can be calculated from complex winding models and or measured. It will always be highest near the core, medium in the middle, and 0 at the outside. No winding curve, no TNT strategy, no taper, or no winder design will change this. It is required by the laws of physics. There are 100 articles, papers, books, and PhD theses in the literature on this topic, as well as in my advanced winding class, so we need not detail that here. The important takeaway is this. If the pressure is greatest at or just above the core, then the width must also be wider due to Poisson expansion. The roll edge will roughly resemble the pressure curve, with the possible exception just above the core, because the core itself resists the expansion of the layers just above it. Everyone wants to be granted an exemption for their product. Well, there are 4 exceptions allowed by physics. The first we've already mentioned, that is a netting product such as snow fences and pull-through meshes, for reasons we don't need to detail here. For the rest of us who are not winding netting, you have 3 remaining options for perfectly flat ends. The first is to wind with absolutely no tightness. Thus, 0, not merely low tension. Thus, 0, not merely low nip. Of course, that is impossible in the real world. What we can do is minimize the tightness and hope that the result will satisfy your customer. The second exception involves fairly complex slitter section design or redesign. For example, if you have automated slitter positioning systems, the computer program can be written to move the slitters ever so slightly from narrow to wide as the winding of the set progressed in a shape similar to the pressure curve. Alternatively, you could design bustle wheels to impinge on the web run between the slitters and thus change the width, again in a program fashion. Of course, you will need to have an overpowered spreader to follow it to be able to handle the width increase as the web flattens, in addition to its normal duty of adding gaps between the lanes. However, in addition to the obvious mechanical and control complexity of this solution allowed by physics, you may end up with some amount of uneven web width as it is unwound, even if the roll themselves are flat. There is one final solution allowed by the laws of physics, that is to saw the roll edges, as is done in some products like tissue. However, you will then end up with uneven web width, just like solution number 2. The point here is to illustrate the principle of DFM, design for manufacturability. Physics requires a certain amount of roll width variation, and thus flared roll edges, and this amount varies a fair amount with the web's properties. You must design that width variation into product and customer specifications so that you don't try and do the impossible. Thank you so very much for joining me in this defect solving and defect preventing series. I hope this has given you some ideas on how to troubleshoot and remedy the root causes for flared roll edges. Stay tuned for the next clip where we will talk about static electricity. If you have a defect you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.